The solubility equilibrium. Not all ionic compounds are equally soluble, and this is due to certain factors, and obviously things like temperature and pressure change the solubility of an ionic compound. The dissociation into its ions is a reversible system. For example, calcium chloride would form calcium 2+ ions and 2 chlorine- ions, but could then, in a reversed reaction, form the solid and precipitate from that solution. The equilibrium is reached between the solid substance and the dissolved ions at its saturation point. All of this was briefly discussed in the first video where I introduced equilibrium. We're going to discuss some of the quantitative properties of the solubility product, which can lead into conversations about the common ion effect. So the solubility product is given the symbol KSP. So it's an equilibrium constant for equilibrium solubility. In this example, we have silver dissolving into silver and chlorine ions, and this arrow here is annoying and in the way, but we're moving on. The constant for an equilibrium product would be the products over the reactant, but in our case, AgCl is a solid, so it doesn't have a concentration. So the solubility product is defined by that equilibrium factor times whatever the solid may be, and given that the KSP is just the multiplied concentration of the ions. So that's the definition of the solubility product. Let's do an easy example here, and we're going to define one more term, molar solubility. So it says lead 2 chloride has a molar solubility of 1.62 times 10 to the negative 2 moles per liter at 25 degrees Celsius. What is the KSP of this salt? So notice that molar solubility has a unit, and it's moles per liter. And this is how much of a specific mole of an ion in the compound could be dissolved. And let's write the chemical equation where you have lead chloride breaking into its ions. The KSP would then be lead times chlorine ions squared, because just like in all other equilibrium problems, that coefficient will be an exponent. And then, given those x values there, you have x and 2x squared. X is the molar solubility, because you have 1 mole of lead and 2 moles of chlorine dissolved for every single mole of solid lead chloride. And the molar solubility in this case is given in the question, and it is X. So we could individually calculate the concentration of each of these ions by just multiplying the chlorine ion concentration by 2. You could also do math here and just combine like terms, and you'd have 4x cubed, and then just plug the molar solubility in for x, cube it, multiply it by 4, and that gives you your KSP. So once you do this value, once you plug these values in and do the calculation, you should get the KSP of lead 2 chloride is 1.70 times 10 to the negative 5. KSP, like all other equilibrium constants, will not have a unit. We're going to come back to this situation in my last example, so remember that it's 1.7 times 10 to the negative 5 for the KSP of lead 2 chloride. Let's look at a second example. What is the KSP of silver chloride? The KSP of silver chloride is given, and now we're going to find the molar solubility. So this could be a question where you would look up a standard table. KSPs at certain temperatures could be provided, and then we set up the equation. You could do an ice chart for these, but your reactants don't have any value because there's no concentration of your solid. So you're just left with the KSP is going to be equal to x squared. Thus, in this case, because it's an ion dissociation at a 1-to-1 ratio, giving 1 cation and 1 anion, you take the square root of the KSP to get the molar solubility, which is 1.34 times 10 to the negative 5 moles per liter. The KSP depends on the solubility of the salt. So larger KSPs at equilibrium means that the salt is very soluble, and small KSPs means that the salt has very low solubility. You could use a value that you call the QSP to figure out if at some point in the reaction will a precipitate form. The QSP, if the KSP is larger than the QSP, then you would shift to be dissolving the solid and no precipitate would form. If the QSP is larger than the KSP, then a precipitate will form because the reverse reaction would be occurring and you would have the solid precipitating. And if they're equal, you're at the saturation point. There's no precipitate, and you're at the saturation point, to be redundant. So in this third example, we're going to look at an example using the QSP. So it says, will precipitate form if a solution of calcium sulfate is made such that the concentration of calcium ions is 0.0104 moles per liter and the concentration of sulfate ions is 0.0082 moles per liter. The KSP is given, it's 7.1 times 10 to the negative 5. So you write the equilibrium expression, the cation and anion dissociate in a 1-to-1 ratio. The QSP is set up, therefore, just the multiplication of the ion concentrations. The two concentrations given are then multiplied together to get 8.528 times 10 to the negative 5. That value is larger than the KSP, and thus a precipitate will form in this scenario. Okay, we're going to look at the common ion effect. So what this means is if you're trying to dissolve, let's say, a solution of lead, let's say lead carbonate in water versus a solution of lead carbonate in a sodium carbonate solution, the solubilities will be different because that common ion, the carbonate in this example, already exists in the sodium carbonate salt solution, whereas in just distilled water there would be no ion concentration present. Adding an ion to a solution that already contains that ion will affect the solubility. The equilibrium shifts away from the ion. Think of Le Chatelier's principle. If you're adding product, it would shift towards the reactant. In a solubility equilibrium expression, the ions are the products. So if you're in a solution where you already have a concentration of that ion, you're going to shift towards the solid, meaning that it will be less soluble in a solution where there's already that ion existing. Here is an image showing the shift of lead chromate that is added to a sodium chromate solution. The common ion, chromate, causes that equilibrium to shift, and the solubility decreases, causing more precipitate to form. And that can be shown up here, the more precipitate forming, which would be more solid lead chromate. Looking at that example, think of this as an equilibrium shift. The number here increases, so if this increases, to reach the KSP, your lead would have to go down. And that lead goes down by forming more of the solid, which would precipitate into the solution, since the KSP is always a constant. Here's a simple example. Let's remember that in our first example we talked about lead chloride dissolving in water, and the KSP of that lead chloride was given. So now we're going to attempt to dissolve lead chloride in a 0.1 molar solution of sodium chloride and see what happens to those ions. X is going to be defined as the concentration of lead ions because that is our variable that is not known. The chloride ions in sodium chloride is 0.10, so we know that concentration. The calculations are different than the standard KSP problems because you have a common ion. In calculations like this, it can be assumed that concentrations of the common ion are entirely due to the solution. That simplifies this calculation. This is a fairly concentrated solution in comparison to lead chloride's KSP. So you can look at those numbers to make sure that that's the case. But clearly sodium chloride is much more soluble than lead chloride, and the chloride ion concentration provided by sodium chloride is much greater than you would ever have in a solution of lead chloride. And just comparing that KSP, you can indicate that because the KSP is much smaller. I believe it was 1.7 times 10 to the negative 5. So, yes, we can assume that the chlorine ion concentration is 0.1 molar, and then plug that value in to solve for X. That X is the then lead ion concentration, and then you compare that to the saturated solution. So in our original solution, the lead concentration was 0.0162, and in the solution of 0.1 molar sodium chloride, it's 0.0017. The concentration of lead ions has decreased by a factor of about 10. If more concentrated solutions of sodium chloride are used, the solubility will continue to decrease.